Okay, welcome everybody to the online virtual seminar of the International Institute of Physics. So despite the world is opening, it is still nice to see here many people with us. And today our speaker is Robert Brandenberger from McGill University in Montreal. So Robert will open the first talk of the second semester of 2022. So let me briefly introduce Robert. He graduated from ETH Zurich in Switzerland, and he received his PhD from Harvard University. He spent some time as a postdoc at Cambridge and at the University of California at Santa Barbara. And since 1987 till 2004, he was a faculty at Brown University. And after that, he moved to McGill, where he stays until these days. Robert is a theoretical cosmologist, and he worked on different aspects of cosmology, but he is also known for application of string theory methods to cosmology, such as inflationary model known as string gas cosmology. For his contribution to physics, he received different awards and prizes, including the Alfred Sloan Fellowship and the prize of the Canadian Association of Physicists in Theoretical and Mathematical Physics. So it's a great pleasure to have Robert with us. Thank you very much for accepting our invitation. And I pass the word to you.
Great. The screen. Is it good? You can see the slides and the cursor?
We can see the screen and the pointer.
So first of all, thank you very much for the invitation to speak and for the nice introduction. So I want to tell you a line of research which I'm very excited about right now. And this is an approach to obtain space-time and early universe cosmology, all from a proposed non-perturbative definition of superstring theory, namely a particular matrix theory. So, but let me first set the stage. So you probably all know that the current scenario of early universe cosmology is the inflationary scenario. And inflation is usually analyzed using an effective field theory framework. So we take Einstein's theory of space and time, and we take classical fields to be the matter in this space and time. Now, as I will try to convince you, there are fundamental conceptual problems for effective field theory description of an expanding universe, in particular, a rapidly expanding universe. And these are not just minor problems, but it's a unitarity problem and inconsistency with the second law of thermodynamics. So I'll persuade you of these two bullet points. So if I manage to persuade you, then obviously we need to look beyond an effective field theory description if we want to understand the early universe. So, and then I will present you with one approach to try to go beyond an effective field theory description of space-time and matter, namely matrix theory cosmology. And I will try to show you what might turn out in those models. But there's going to be a caveat to this last section. And the caveat is that I am not a string theorist. I am just using string theory results. So string theorists might find in this last section of the talk things which are not so kosher. So this is the outline of the talk. I will first talk about these conceptual problems for using effective field theory techniques in a rapidly expanding universe. So that's the first section. Then I will remind you that there's more than one early universe scenario which is consistent with the data, not just inflation. And I will give you criteria for a successful early universe cosmology. So and then I will turn to our actual work, which is to get an emergent cosmology from matrix theory. So this is the outline. Good. So let me start with this graph, which Jerome Martin and myself presented about 20 years ago in the context of what we were arguing to be a Trans-Planckian problem for inflation. So here you see a space-time sketch. The vertical axis is time. The horizontal axis is physical distance. And the time interval between T sub I and T sub R, that's the period of inflation. And here in this space-time sketch, I sketch 3 length scales. First of all, the horizon. And the horizon is defined as the forward light cone of a point on the initial Cauchy surface. So a point right here. Now, during the period of inflation, when space expands exponentially, the horizon expands exponentially as well. So the second length scale, which I plot, is the Hubble radius, which is defined as the inverse expansion rate. Now, during the period of inflation, the expansion rate is constant, and therefore the Hubble radius is constant. After inflation, the Hubble radius starts increasing linearly. So what is crucial about inflation is that it generates an exponential difference between horizon and Hubble radius. Now, the third length scale, which I plot, is the physical length, which corresponds to some small amplitude fluctuation of density in this expanding universe. And in the period when space expands exponentially, the wavelength of this fluctuation also expands exponentially. So this is this red curve labeled by K. K for co-moving momentum. Now, the reason why inflation is successful at providing a mechanism for the origin of structure in the universe is that scales that we observe today start out smaller than the Hubble radius at the beginning of inflation. So the fact that this red curve dips below the Hubble scale, that's a crucial ingredient that makes inflation successful. But what we pointed out 20 years ago is that if inflation lasts only a little bit longer than it has to in order to be successful at solving the horizon problem, then the length scale of things that we observe today starts out smaller than the Planck length at the beginning of inflation. And that means it starts in a region where we cannot trust classical gravity and we cannot trust classical effective field theory. So we argued 20 years ago that in the context of inflation, there is a breakdown of effective field theory. Now, 3 years ago, Bedroya and Waffer turned this space-time diagram into a new conjecture. So their conjecture states that no quantum gravity model can have the feature that trans-Planckian modes ever exit the Hubble horizon. So going back here, you see the problem here is that trans-Planckian modes are exiting the Hubble horizon. So Bedroya and Waffer, they postulate that this cannot happen in any consistent quantum gravity model. So what does this mean mathematically? So if we take our space-time metric to be given in the usual Friedmann-Robertson-Walker-Lemaitre form, T is time, X are my co-moving coordinates, A of T is the scale factor, which gives the extent of space, H is the expansion rate, the inverse of which is a Hubble radius. So the Trans-Planckian censorship conjecture, the TCC, says that if you start at any initial time T sub I with the Planck length and let this scale expand until some later time T sub R, you always have to remain smaller than the Hubble radius. So this is a mathematical form of the Trans-Planckian censorship conjecture. So now I'll give you 3 justifications for this Trans-Planckian censorship conjecture. The first one is an analogy with Penrose's black hole cosmic censorship hypothesis. So Penrose starts with the picture that black holes with charge smaller in the mass, they have a singularity, but the observer out away from the center of the black hole is shielded from the bad stuff that happens at the singularity by a horizon. Now, the Einstein equations, as an effective field theory, they allow for solutions with charge greater than a mass. And for those solutions of the effective field theory, the observer far away from the center of the black hole is not hidden, or the singularity is not hidden from this observer. This observer can sense the bad stuff that happens at the singularity. So Penrose postulated that although the effective field theory of general relativity allows for these pathological solutions for which the Cauchy problem is not well defined and for which there are unitarity problems. So he conjectured that the theory that completes general relativity cannot have these features. All singularities must be shielded by horizons. So this is Penrose's cosmic censorship hypothesis. Now let's translate this to cosmology. Position space becomes momentum space. The black hole singularity becomes the set of Trans-Planckian modes. And I replace the black hole horizon by the Hubble horizon. And so Penrose translated to cosmology now is a statement that an observer measuring only super Hubble horizon modes must be shielded from the bad stuff, from the Trans-Planckian modes. So this is the first justification of the Trans-Planckian censorship conjecture. Now, in this analysis, I haven't justified why I take the Hubble horizon as the crucial length scale. And to do that, I remind you that fluctuations, energy density fluctuations, gravitational waves, they don't grow when the wavelength is smaller than the Hubble horizon. They only oscillate. And these fluctuations freeze out, become squeeze states, and classicalize on super Hubble scales. So in my formulation of the Trans-Planckian censorship conjecture, we are making a very conservative assumption that it is only the classical region which we demand to be insensitive to the Trans-Planckian region. Maybe there should be actually a more restrictive version of the TCC. Okay. Now, to the second problem, the second justification of the TCC, this is a unitarity issue. So as pointed out by Nathan Weiss a long time ago and brought up again in a recent paper by Kotler and Strominger, an effective field theory in an expanded universe is intrinsically non-unitary. And I'll become now a little bit more specific in terms of what I mean by effective field theory. I will take a very conservative view of effective field theory. I will say that fields are expanded in harmonic oscillators, and it is each co-moving wave, which is a harmonic oscillator, and each of these harmonic oscillators is quantized. So this is what I mean by effective field theory. Now, in order to avoid the Planck catastrophe, we have to impose an ultraviolet cutoff. And this cutoff has to be on a fixed physical wavelength. And to maintain a fixed physical wavelength of the ultraviolet cutoff in an expanded universe, I have to continuously create co-moving modes. So this is extreme non-unitarity. The dimension of a Hilbert space is increasing as a function of time. So demanding that the classical region be insensitive to this non-unitarity gives us precisely the Trans-Planckian censorship conjecture. So this is a second justification of the Trans-Planckian censorship conjecture. And now an aside, which I'll come back to at the very end of the talk, is the following. When we talk about the cosmological constant problem in cosmology, this comes from treating matter using effective fields. Because what we do in when we talk about the cosmological problem is we take each field, we expand the fields in co-moving Fourier modes, we quantize each Fourier mode like a harmonic oscillator. Each harmonic oscillator has a ground state energy. We add up the ground state energies and we get the cosmological constant problem. I will maintain that this usual view of the cosmological constant problem is an artifact of the effective field theory analysis. And in our matrix cosmology, which I'll present at the end of the talk, there is no cosmological constant problem. There is nothing that looks like a cosmological constant which gravitates. That's the result of the analysis. But now I'll turn to the third justification of the TCC, and this is an entropy analysis. Now, those of you who work on string theory will know that there's been lots of discussion about the entanglement between sub and super Hubble modes for black holes. Now, in analogy, there's entanglement entropy between sub and super Hubble modes in cosmology. And if we take a phase of accelerated expansion, the phase space of super Hubble modes is increasing, and therefore the entanglement entropy density is increasing. Now, if we demand that the entanglement entropy density that builds up during inflation remains smaller than the post-inflationary thermal entropy density, then you find precisely the Trans-Planckian censorship conjecture. So bottom line is that if you violate the Trans-Planckian censorship conjecture, you have unitarity problems and you violate the second law of thermodynamics. Now, what does the TCC imply for inflation? So this is my space-time sketch of inflation. Again, this is a period of inflation. This is the post-inflationary period. This is the present time, end of inflation, beginning of inflation. This is the Planck length. This is the Hubble horizon. And this curve here indicates the physical wavelength of a density fluctuation mode. For example, that corresponds to the quadrupole of the cosmic microwave background. So now the TCC says that if at the beginning of inflation, we start with the Planck length, this length cannot expand to becoming bigger than the Hubble radius at the end of inflation. And I show this criterion to be marginally satisfied in this sketch. So the TCC imposes an upper bound on the duration of inflation. Now, if inflation is to be successful, then scales that we observe today have to originate on sub-Hubble scales at the beginning of inflation. That sets a lower bound on the duration of inflation. And I showed this criterion to be marginally satisfied in this sketch. Now, whether the upper bound on the duration of inflation due to the TCC and the lower bound on the duration of inflation by demanding that our current Hubble horizon starts out inside the Hubble horizon at the beginning of inflation, whether these two are consistent depends on where the Hubble radius is relative to the Planck length. The higher the scale of inflation, the closer the Hubble horizon is to the Planck length, and the more difficult it is to reconcile these two criteria. So let's do the mathematics. This is the TCC bound, the upper bound on the duration of inflation. T sub star is the beginning of inflation. T sub r is the end of inflation. This is a lower bound on the duration of inflation by demanding that the current Hubble radius starts out inside the Hubble radius at the beginning of inflation. So these are the two conditions. And if you do a simple algebra, you find that they are only consistent if the energy scale of inflation is less than about 3 times 10 to the 9 GeV, which is about 5 orders of magnitude smaller than what is usually assumed. Now, if you have a model of inflation with this energy scale, then the induced gravitational waves are negligibly small in amplitude. The amplitude of gravitational waves divided by the amplitude of density perturbations is smaller than 10 to the minus 30. So in inflationary models, which are consistent with the Trans-Planckian censorship conjecture, you are forced to have a very low inflation, and hence you predict vanishing primordial tensor modes. And for those of you who hear cosmology talks, you will often hear the statement that discovering gravitational waves using B-mode polarization is the smoking gun for inflation. Nothing could be further from the truth. In models of inflation, which are consistent with the TCC, you predict vanishing primordial gravitational waves, because this means for experimental purposes, vanishing. Okay. Now, for late-time cosmology, the TCC also has implications. It means that dark energy cannot be a bare cosmological constant. The same conclusion that you also get from the swampland constraints. Okay. So now let me turn to discussing scenarios for successful early universe cosmology. Because I've told you that if you buy the Trans-Planckian censorship conjecture, this is bad news for standard inflation. But we do not need inflation. So this is the data that we need to explain. So this is the spectrum, the angular power spectrum of microwave anisotropies. So horizontal axis is angular scale, small angular scales, large angular scales. And the vertical axis is the power of the fluctuations on the corresponding angular scales. And the black dots, those are the data from the WMAP experiment. And you see on small angular scales, there's some statistical errors. On large angular scales, there's a cosmic variance, a systematic uncertainty. And here there's this red curve, which fits the data beautifully. And now I'm going to tell you who first discussed all of these features of this red curve. And the people who discussed the beautiful features of this red curve were Zeldovich and Zunyaev and Peebles and Yu in about 1970, which is 10 years before the development of inflationary cosmology. 10 years before the development of cosmology, this curve was well understood. So this is a reproduction of a figure from the Zeldovich-Zunyaev paper of 1970. Vertical axis is time. Horizontal axis is co-moving length scale. And this diagonal black curve is the Hubble horizon, which is also the Jeans length, at times before the time of recombination. This is the time when the microwave background is released. So now what Zeldovich and Zunyaev, and in parallel Peebles and Yu argued, is that if you start out with fluctuations on all length scales larger than the horizon, then these fluctuations are frozen in until the scale crosses the Hubble horizon, and then they start to oscillate. So this is known from the theory of cosmological perturbations. Fluctuations are frozen in. If the length scale is larger than the Hubble horizon, they oscillate on sub-Hubble scales. So now, if you start out with these fluctuations on all scales, they are standing waves outside of the Hubble radius, then the mode that enters the Hubble radius right at recombination, we catch this when it's a standing wave with maximal amplitude. So it will induce maximal amount of microwave anisotropies. Whereas a mode which has done 1/4 of an oscillation, we catch it at a node, only a velocity perturbation, and it's a relative minimum of the temperature fluctuation, and so on. So this picture that you see here, this reproduces this red curve. And to get the angular scale and the amplitude and these particular features of this red curve, you have to tune a couple of parameters. For example, the matter energy density, the initial spectrum of these density perturbations. The same 6 parameters that you have in standard cosmology, These are 6 parameters which are completely independent of inflationary cosmology. So what I just try to convince you of is that given a scale invariant power spectrum of fluctuations on scales which are super Hubble horizon before equal matter and radiation, that then you will produce the acoustic oscillations in the CMB angular power spectrum, which were detected. And well, this figure in the Zeldovich-Zuniaev paper as a second part, and this is the matter power spectrum as a function of wave number. And these oscillations also impart oscillations in the matter power spectrum. These are the so-called baryonic oscillations. So all of these nice features, the CMB angular power spectrum and the baryon acoustic oscillations in the matter power spectrum were predicted. The physics was well understood 10 years before the development of inflation, as long as you have a mechanism to produce an approximately scale invariant power spectrum of fluctuations before equal matter and radiation. Okay. So now come the 3 criteria for any successful early universe scenario. So the first is that the horizon is much bigger than the Hubble radius. Otherwise, we can't produce the approximate isotropy of the microwave background. The second condition is that scales which we observe today have to originate inside the Hubble radius at some early time. Otherwise, we can't have a locally causal mechanism to produce the fluctuations. And finally, the mechanism the model which obeys the first 2 criteria also has to have a mechanism for producing approximately scale invariant curvature fluctuations. Scale invariant means the same power on different wavelengths. And by power, I mean in a very specific way, which I might come back to towards the end of the talk. So these are the 3 criteria for any successful early universe cosmology. And I will now give you 3 cosmological paradigms which satisfy these 3 criteria. The first is inflation. So you've seen this space-time diagram already twice. Period of inflation, exponential expansion space, the horizon becomes exponentially larger than the Hubble radius. Criterion 1 satisfied. If inflation is long enough, scales which we observe today start out sub-Hubble. Criterion 2 satisfied. The fact that the energy density during inflation is approximately constant guarantees the approximate scale invariance of the cosmological fluctuations. Criterion 3 satisfied. Now, the second scenario is a bouncing cosmology. So a bouncing cosmology is a cosmology in which the scale factor starts out in a contracting phase, and then there's some new physics that gives transition from contraction to expansion, and then you have standard Big Bang expansion. So standard Big Bang expansion, the mirror inverse of this standard Big Bang-like contraction, and some new physics that gives us a bounce. So this is the assumption that goes into bouncing cosmologies. And here, in this top figure, is a corresponding space-time graph. Time, space, co-moving spatial coordinates. The bounce point, phase of standard Big Bang expansion, the mirror phase. Now, the horizon is infinite because time runs from minus infinity to plus infinity. Criterion 1 satisfied. Here I plot the Hubble radius, the inverse expansion rate, mirror inverse between expanding and contracting. And here are 2 co-moving scales. And so you see that if you go far enough back into the past, scales that we observe today start out sub-Hubble. Criterion 2 satisfied. Now it turns out that if you start with vacuum fluctuations in this phase, and you look at length scales that exit the Hubble radius in a matter-dominated phase of contraction, then the vacuum fluctuations are translated into scale invariant fluctuations. That you have to accept what I'm telling you here. If you can ask questions later on. So this is another way of satisfying all three requirements for successful universe cosmology. But the matrix cosmology will actually be a realization of the emergent universe scenario. And the emergent universe scenario is a scenario where, before some time, which I call T sub r, there might not even be a space-time description. Or if there is a space-time description, I will model it as being something which is quasi-static. So there's an emergent phase, a phase transition to the standard Big Bang phase of expansion. So this is a postulate of the emergent universe scenario. This is a corresponding space-time sketch. So time, physical length scale. This is the emergent phase. This is a phase of standard Big Bang expansion. So the emergent phase lasts from -infinity to this phase transition time. So the horizon is infinite. Criterion 1 satisfied. The emergent phase is quasi-static, so the Hubble radius is infinite. So scales that we observe today are sub-Hubble in the emergent phase. Criterion 2 satisfied. And it turns out, and this I will show you towards the end of the talk, that if you start out with thermal fluctuations, which have holographic scaling in this emergent phase, then that generates scale invariant curvature perturbations and gravitational waves. So I'm using thermal fluctuations in the emergent phase with holographic scaling. And these are, one realization of this is thermal fluctuations of a gas of closed strings. So since there are string theorists in the audience, I sort of want to make clear the assumptions that go in here. There's thermal fluctuations and holographic scaling. I'll come back to that later. So the bottom line of this part of the talk is that there is more than one early universe scenario that is consistent with the current data, not only inflation. And so my advice to string theorists is that you, in light of the problems of getting inflation from string theory, in light of the Trans-Planckian censorship conjecture, well, maybe the message is that it is one of the other scenarios which is realized in string theory, specifically the emergent universe scenario. Okay. So now an aside, bouncing cosmologies and emergent cosmologies are trivially consistent with the Trans-Planckian censorship conjecture, as long as the energy scale of the bounce, or the energy scale of the emergent phase, is lower than the Planck scale. It is only the inflationary cosmology which is constrained by the Trans-Planckian censorship conjecture. However, all of these early universe scenarios require going beyond an effective field theory description. So if you like inflation, then you have to go beyond an effective field theory description to get your inflationary phase. If you like a bouncing cosmology, then you have to go beyond an effective field theory to get the bounce. And if you like an emergent scenario, then you have to go beyond an effective field theory description to give you the dynamics of the emergent phase. So in all of these scenarios, you have to go beyond effective field theory. Okay, so now at this point, there comes a transition. Everything that I've said so far, I think, is robust. And I'm very confident of everything I've said so far. And now comes a transition to the point where I'm not confident about the things that I'm going to tell you about. Because now I'm going to start by exploring a particular model which goes beyond effective field theory. This is this matrix theory model. And I'm not a superstring theory expert. And so I'm less confident about the reliability of what I'll present. But I think it's sufficiently interesting that I'll still present it. And in fact, I'm very keen on presenting it because I'm excited about the prospects. Okay, so our starting point here is the BFSS matrix model. So this is a matrix model which was proposed in 1996, 1997. It was proposed as a non-perturbative definition of superstring theory. So it is a model, it is a quantum mechanical model, which involves n by n Hermitian matrices and a set of 10 n by n Hermitian matrices. Now, there's no space, and therefore no singularities in this matrix model. There's a Lagrangian, so this matrix model is given by a Lagrangian, and there's time. So in this last line, I sort of state that it is in the capital N going to infinity limit, the limit taken in a particular way. This is the limit in which you are supposed to get superstring theory. And this is supported by perturbative calculations on the matrix model side compared to perturbative calculations on the superstring side. Okay, so this is the Lagrangian of this matrix model. So Lagrangian, there's a coupling constant, string coupling constant. There are 9 xi matrices, n by n matrices. There's something that looks like a kinetic term. There's something that looks like a potential term, the commutator here. And this d sub t is something that looks like a covariant derivative operator. It is the partial derivative with respect to time plus the commutator with a matrix A sub 0. This is the 10th matrix that appears, also an n by n Hermitian matrix. And here I specify the limit in which we are supposed to recover superstring theory. So this is the Lagrangian of the model that I'll be considering. Okay, now I will be considering this model in a high temperature state, in a fixed high temperature state. So at this point, we have a state, we have no space, and no evolution. Now it turns out that at high temperature, the bosonic sector of the Euclidean version of this model is well approximated by the bosonic sector of a different matrix model, the IKKT matrix model. I'll give you the action of that in a minute. And by well approximate, I mean the following thing. So you take the action for the BFSS matrix model, which is given by this Lagrangian, and I will expand all of these 9 matrices in Matsubara frequencies. And at high temperatures, it's the time-independent mode that dominates the action. So the contribution of the of the small n equals 0 modes, that goes into this first term in the action, and all the other terms give me the 1 over capital T corrections. So this dominant term is a term that contains matrices that have the small n equals to 0 matrices from here, and the A0 matrix. And the action for the 0 modes has this formula. And this is the action of the matrix model that was proposed by Ishibashi, Kawai, Kitazawa, and Uchiha, also in 1997, as a non-perturbative definition of type 2B superstring theory. Okay, so this is our starting point. Good, so now I'm slowing down because I want to focus on the way that our construction works. So these are all Hermitian matrices, so we can work in a basis in which one of these is diagonal, and we will work in a basis in which the temporal matrix is diagonal. Let me go back a couple of slides, this slide. Implicit in this action is the fact that there's an eta AB symbol, the Minkowski eta AB symbol, which is used to raise and lower indices. So this action for the IKKT matrix model and the corresponding Lagrangian for BFSS, it contains microcausality. That's already inbuilt. So I'm not getting emergent causality out of this construction. Local causality is built into the starting point. Space and time is. So going back, I'm working on the basis in which the temporal matrix is diagonal, and I will call the matrix elements, the eigenvalues of the temporal matrix, they will be my time values. So now, from numerical studies of this IKKT matrix model, you know that in the large n limit, the expectation value, the quantum mechanical expectation value of the trace of A naught square scales as kappa times capital N. Kappa is some small number. And this implies that the maximal eigenvalue scales as square root of capital N. So as capital N goes to infinity, I get a time range that goes to infinity. In fact, there are positive and negative eigenvalues, symmetrically distributed. And so therefore, the time that emerges goes from minus infinity to plus infinity. And now the separation between temporal elements goes as 1 over square root of capital N. So the conclusion is that in the capital N going to infinity limit, I'm getting infinite continuous time, infinite in the past and in the future. Unlike what you have in inflationary cosmology, identical to what you have in bouncing and emergent cosmologies. Okay, so this is time. So now let's turn to the spatial matrices. Now, from an analytical analysis of the IKKT action, you find that if you look at the spatial matrices, AI square, AI, and if you look at the matrix elements, AB of these AI matrices, and when you go away from the diagonal, that then the expectation value of these decays if you go sufficiently far away from the diagonal. You find that using the Riemann-Lebesgue lemma, you find that analytically. So we have analytical evidence for this statement here. Now, there's numerical evidence that if you don't go very far away from the diagonal, that the matrix elements are approximately constant. And this n sub c scales as square root of capital N. So we have analytical understanding of this, analytical understanding of the third point, but only numerical understanding of the fourth point. Okay, so now what I will do is I will now propose a way to get emergent space out of the matrix model. Space at a particular time. So I continue to work in the basis in which A naught is diagonal. So I go a distance down the diagonal where I have a particular temporal eigenvalue t. And at that position on the diagonal, I look at the spatial matrices. This is illustrated here. So I have my time. I go down, I put myself at a particular time, and then I look at the small blocks of the corresponding spatial matrices localized the same position along the diagonal. So I look at these small matrices, and their dimension is small n by small n, with the center at the point depending on the time. So I'm going to get space at a particular time from these sub-matrices positioned at a particular position along the diagonal. Good. So now I can identify the extent of space in the ith direction by taking these small sub-matrices localized at a particular value of time. That gives me the extent of space parameter. And here I'm following what Nishimura and his collaborators have been doing for a decade. So now it's been observed numerically that in a thermal state, there's spontaneous symmetry breaking. The SO of these 9 spatial matrices is spontaneously broken to SO6 cross SO3. These accelerated space parameters only become large in 3 out of the 9 dimensions. It's interesting because we live in 3 dimensions. So this phase transition was found in numerical simulations, and it was confirmed using Gaussian approximations. Now, the physical reason for this phase transition is something which Waffa and I already understood back in 1989. And this is the fact that in these matrix models, in these matrix configurations, there are embedded strings, string configurations as solitons. And these solitons can only break in 3 large spatial dimensions, not more than 3 large spatial dimensions, simple dimension counting. And therefore, this will only allow 3 spatial dimensions to expand. So this is the physical intuition for this. This remains to be explicitly worked out, but I'm very confident about this statement. Anyway, so now we have 3 large dimensions, 6 small dimensions. And what we will do is we will now define my small n as my co-moving coordinate, and the size of the matrix of dimension n by n, we will define that as physical length. So physical length of a curve between n equals 0 and n, this is the way it's defined. N is my co-moving coordinate. And if I have co-moving coordinate and physical length, I have the metric. The metric is defined in this way. So with this prescription of co-moving coordinates and length, I not only get emergent, continuous, and infinite space, but I also get a spatial metric. And using the features of these matrices for small n, I find that the matrix is spatially flat and independent, which means that there's no flatness problem in this model. So at this point, you see we have emergent time, continuous and infinite, emergent space, continuous and infinite, and an emergent metric, at least the spatial part of the emergent metric, which is spatially flat. Now, if you look at classical solutions of the matrix model at large spatial, at large extent of space, then you find that the scale factor, the thing which appears in the metric here, that this grows like in a radiation-dominated universe. So in particular, there's no sign of a cosmological constant. We are never quantizing harmonic oscillators, so there's no harmonic oscillator ground state energy to subtract. And in this matrix model, there is indeed nothing that looks like a cosmological constant which gravitates. Okay, so now, so far, I've only talked about what we get from the 0 modes of the BFSS matrix model. Let's look at the contributions of the finite temperature corrections, the 1/T corrections. Good. So we've, in our work on string gas cosmology done in 2006, 2007, we know how to compute thermal density perturbations and thermally induced gravitational waves from thermal initial conditions. We can get density perturbations and gravitational waves by calculating thermal correlation functions. So this part of the calculation, we imitated what Nayeri, Patel, Waffa, and myself did 15 years ago. So we consider the BFSS finite temperature partition function, including the 1/T corrections. We take partial derivatives of this finite temperature partition function with respect to temperature. That gives us a specific heat capacity. That gives us the density perturbations. We take the partial derivatives with respect to the extent of space parameter. That gives us the pressure perturbations. That gives us the gravitational. And what we find is, like in string gas cosmology, we get a scale-invariant spectrum of curvature perturbations with a Poisson contribution on ultraviolet scales and a scale-invariant spectrum of gravitational waves, with an amplitude which is given by the ratio of the string scale to the Planck scale. And if you take the string scale based on the textbook of Green, Schwartz, and Witten from heterotic string phenomenology, you get exactly the right amplitude to agree with observations. So what we find is, we find that in this BFSS matrix model, that we can extract emergent infinite space, emergent infinite continuous time, an emergent spatially flat metric, and an emergent Early universe phase, which gives us thermal fluctuations leading to scale-invariant curvature perturbations and gravitational waves. So at this point, you see we have a proposal of an Early universe cosmology, which not only reproduces the stuff which inflation does, but it qualitatively does much more. It gives us emergent space, emergent time. It gives us, there's no cosmological constant. So this is qualitatively more ambitious. Obviously, there could be mistakes. I'm going out on the limb here. Okay, so now there are lots of open problems, obviously. We need to understand the phase transition from the emergent phase to the expanding phase much better than we do. And it is only once we understand this transition that we can calculate the deviations of the spectrum of density perturbations and gravitational waves from being exactly scale-invariant. So what cosmologists call the spectral indices, we want to compute them, and we will compute them, but we will need a better understanding of this phase transition. Now, in what I presented today, we focused on the bosonic sector of these supersymmetric matrix models. This does not contain what is now matter in the universe. So we need to include the contribution of the fermionic sector. And that will then give us a universe which has both a radiation phase and a matter-dominated phase of cosmology. And if we are lucky, we will also get a new picture of dark energy emerging from it. So there's lots of things to do. So there are lots of open problems. So I don't want to go over time. I want to actually end before an hour's over to leave time for questions. So I want to go back to the main conclusions. So there are sort of robust conclusions, which I hope to have persuaded you of. Namely, inflation is not the only scenario of early universe cosmology, which is consistent with current data. And the second conclusion is that in light of the Trans-Planckian censorship conjecture and other conceptual problems, for example, the swampland constraints, effective field theory models of inflation are not viable. This does not mean that inflation is not viable, but you have to go beyond effective field theory. And there are people like Dvali and collaborators, or my colleague Keshav Dasgupta and his collaborators, who are working on getting models of inflation from non-perturbative understanding of an inflationary phase emerging from string theory. But in what they get is they always get short duration inflationary phases. In particular, in the work of Dasgupta et al., you get transient inflationary phases in agreement with the Trans-Planckian censorship conjecture. So in light of the TCC, dark energy cannot be a cosmological constant. And we need to go beyond effective point particle theory if we want to understand the very early universe. So I hope I've persuaded everyone in the audience of this. And so now if you are persuaded by this, then obviously you have to go beyond effective point particle theories. And I've presented to you an approach to trying to do this based on a particular model, the BFSS matrix model, which was proposed more than 20 years ago as a non-perturbative definition of superstring theory. And the preliminary evidence is very encouraging. We seem to get emergent time, emergent space, and emergent metric, which is spatially flat. And thermal fluctuations give us scalar spectra of cosmological perturbations and gravitational waves. And all these problems of standard Big Bang cosmology are trivially solved without requiring inflation. So thanks for your attention, and I will go back to the robust conclusions. And I'd be happy to answer questions.
Okay, thank you very much, Robert, for this very interesting. We already have some questions, so let us think. Let us start from Shikulo Stoza first. Please ask a question.
Hello, good afternoon, Professor Brandenberger. Thank you for the talk. I have a couple of questions. First, you said, I understand the point about the censorship conjecture kind of constraining inflation instead of fine-tuning on the energy scale, but at the end there you said that the emergence model and the bouncing models don't suffer from that because they already are above the Planck scale.
No, they're not above the Planck scale. So let me go back to...
They are below.
They are below the Planck scale. So,
yeah, but how
so
is
let me,
that not...
let me illustrate this in terms of this graph here. This is the way to answer your question for emergent. So this is a space-time diagram of emergent. So what I'm saying is that if the Hubble length at the bounce point is greater than the Planck length, then you have never any scales exiting no Trans-Planckian scales ever exiting the Hubble horizon.
Yeah, but my question is, how do you make sure of that without, you said yourself that you don't have yet an understanding of the phase transition. How is that not also some kind of fine tuning?
Okay, so you see, we understand the energy scale at which the transition occurs.
Oh, okay.
But we don't understand the precise form of this curve, which I here drew as continuous. How long is this transition phase? That's what I mean by we don't understand the phase transition. So to first order, the curve will be like here, but we need to have an analytical form for this curve as an expansion around this point.
And in bouncing models, you also know the energy scale of the bounce for some.
That's right. That's right. So you see here again, if the energy scale of the bounce is lower than the Planck scale, then the minimal value of the Hubble radius will be larger than a Planck length.
Okay. Okay.
And so again, I will need new physics to generate this transition between contraction and expansion.
Okay. And can I ask a second question, Dimitri?
Go ahead.
And you showed a slide before that about the problem with entropy, entanglement entropy between sub-Hubble and super-Hubble modes. And in general, what I've seen, I study bouncing cosmology, we usually talk about it, but don't actually calculate things with the entanglement being, like we consider modes that are unentangled with the background or unentangled with each other. Isn't that entanglement problem a problem for any evolution of modes when you consider that they might be entangled? If you're considering, like in bouncing cosmology, that they might be entangled with each other or with the background, shouldn't that arise as a problem also, both in bouncing and emergent cosmology?
Yes, this is a good point. I take this point. So what we've done here is we in this paper is we computed the reduced density matrix of the super Hubble modes due to their entanglement with the subhubble modes.
Mhm.
And we included leading order nonlinearities coming from the Einstein equations.
Okay.
So this is what we did here, and then we got the conclusions.
Okay.
But indeed, in any cosmological scenario, one should do entropy. One should consider this entanglement entropy, and we have not done it for bouncing and emergent scenarios, to my knowledge.
Thank you, Professor.
Maybe a quick question. So can you discuss this question in the matrix model?
Not yet, because we don't have the see, the level at which we did this calculation is at the level of an effective field theory, because we are about Einstein. So in the matrix model, we don't yet have the effective field theory. So no, I cannot address this question yet. But it's an interesting question.
Okay, there's another question from Edson Moreira. Edson, please ask your question. I also remind you that if you're unable to ask your question through use the microphone, you can also write it in the chat.
I'm just a moment, please. I'm not able to open my camera for some reason, but I released.
No, your camera is open. I see you well.
Okay, thank you very much.
We can hear you also.
Thank you, Professor, for the nice talk. You said that so space and time it comes as emergent object from a statistical mechanics point of view. What would be the interpretation of temperature in this scenario?
Very, very good question. So you see, when we have this matrix model, so in the Euclidean time domain, we can express the matrices in this form. And this is the way in which the temperature enters. So we do Euclidean quantum finite temperature quantum field theory.
But you are supposing that there is a heat bath or something like that in which
no, there's just a state. We have a quantum mechanical system which has many energy states, and the state that we pick is a state in which all of these eigenmodes are excited according to a thermal distribution. So it's a thermal state from the point of view of statistical mechanics applied to this.
So in some sense, space and time would be a consequence of this statistical point of view, statistical mechanics point of view.
No, I don't think so. You see, our space and time are emerging from these zero modes of the matrices. So without a large n limit, we would not be getting continuous space and continuous time. So the space and the time, they come from the eigenvalues of these matrices, the 10 matrices.
So low would be sort of low temperature behavior of the model.
No, it's more like high temperature.
High temperature.
Because it's at high temperature that the corrections to the action are small.
Okay. Thank you. Thanks a lot.
So are there any other questions? Please, Tiago. No, sorry, I think there is another question from Chico.
Yeah, sorry. So is this space-time emergency from string theory some way of also getting the gravitational field emergency? Like you get gravity from that?
Yes, that's the hope. So you see, we have a dynamical evolution of a scale factor. We see the scale, we can define a factor, and the scale factor is not constant in time. And that is something that usual gravity will give us. Now, part of our research program is to actually develop this further and to try to see, is there something like an Einstein action which we can obtain in an emergent way?
So
what is the low energy field theory that can emerge?
You get the scale factor, you get cosmology, but you're not sure if you get the full general relativity.
That's right.
But right. Do you get some kind of quantum field theory for gravity from that? Gravity.
This is so we don't have a graviton yet.
No.
But we have the quantum theory that is giving us the evolution of a scale factor.
Okay.
And there's no in principle obstacle to get the graviton, but it will take a while until we are there.
Yeah, I imagine that.
So there are a number of steps, and the identification of the graviton is one of these steps, and the evolution equation for the gravitons will also be a step.
Hope you are successful.
Yeah.
Well, this looks indeed exciting. Let's see if there are other questions. I
should give credit to my collaborators on this. Shudo Brahma, who's now junior lecturer in Edinburgh, and my student Samuel Laliberté.
Okay. Not sure, Edson, did you raise your hand again, or you just didn't lower your hand? Do you have
not really, Dimitri. Thank you very much. Sorry.
Okay, no problem. So I have a couple of naive questions. So one is, in this discussion of space emergence, this reminded me a little bit the story of ETH, of the eigenstate thermalization hypothesis. I'm not sure there's any connection whatsoever, but I don't know if you can comment on that.
Actually, you see, I've heard the word.
I think this idea that you have so you have a density matrix of your state, but you get a thermal state because the elements on the diagonal, they exponentially enhanced in comparison to the elements off the diagonal. So I thought that would be somehow conclusion here, that's where you're heading here too.
Right, there's definitely an analogy. The matrix elements away from the diagonal, sufficiently far away, they are suppressed, exponentially suppressed in the.
So what determines that? Is it some kind of horizon, or you said it's a physical scale, the size, the scale at which basically this decay starts, right? It is physical scale, but I would say it was.
You know, let me go to. Yeah. So you see that this n sub c goes to infinity. So I don't interpret this as a physical scale. I interpret this as a scale in the construction. So we get it from the matrix model action. Because if you essentially have a Gaussian integral over all of these AI sub AB. And then there is a scale in the action, an energy scale in the action. And that will then determine this n sub c. But then in the capital N going to infinity limit, that scale goes to infinity.
All right.
Now, there was work there in the context of non-critical string theory, the C equals 1 string theory. There was work a long time ago by Justifications does. This is actually the work that inspired me to think about this. They have a theory of a matrix model with one matrix, and they get one spatial dimension. So unfortunately, I'm not familiar with his work on eigenfunction thermalization, but I should be actually.
Well, yeah, I think there's no connection, no direct connection in this case, indeed.
No, it sounds like there may be a connection.
Okay, I think there's another question from Shiko. Is that right?
Yeah, I'm sensing that you are trying to finish the meeting, so I wanted to get one more in before you do.
Sure, go ahead.
Robert, you worked for a while on bouncing models, like the ecpyrotic model.
Yep.
And I was wondering, besides being an interesting alternative, this matrix theory that you're working in now, there were any fundamental problems or caveats to the bouncing models that you've studied that made you kind of change your directions, or it's just another direction? Both are interesting. My question is, what are the problems with bouncing models that I should be worried about?
Yes.
This is actually related. I'm sorry to interrupt you. It is related to my second naive question. So why? I mean, well, of course, cosmology, the inflationary cosmology is very popular. Is the most popular theory, cosmological theory, cosmological models. So why? And now you're telling us that there are actually several alternative models. I guess these other alternative models were not successful in explaining something that inflationary model can.
No, this is actually not the case.
Not the case. Bouncing.
So now let me go back to the question about bouncing cosmology. So if you just take this kind of symmetric bouncing model, then what we called matter bounce, this has serious problems because it is unstable to anisotropies, and it is unstable. So that's the most important problem. So if you have a contracting phase, which is the mirror inverse of our expanding phase, then anisotropies will blow up in the contracting phase, and you basically therefore do not reach a homogeneous bounce. So that's the most important challenge of bouncing models, except for bouncing models of ecpyrotic type. And ecpyrotic cosmologies are cosmologies where the contracting phase is a phase of very slow contraction. And very slow means equation of state, pressure divided by energy density greater than 1, much greater than 1. And from a point of so if you want bouncing cosmologies, those are the ones that you should consider, because the other ones have stability problems. So now, why should one consider ecpyrotic scenarios? One is from the point of view of string theory. We know that there are scalar fields with negative exponential potentials all over the place because anti-de Sitter is the ground state, and generically you get exponential potentials. So now it turns out that a scalar field model with a negative exponential potential gives you ecpyrotic contraction. So this is our recent work on bouncing on the ecpyrotic bouncing models. Now you need to get the bounce. And you need the bounce both to get the transition from contraction to expansion, and you also need to study the bounce in order to get the perturbations right, to compute the perturbations at late times. So now we have a proposal of a stringy S-brane, which gives you the instantaneous transition between contraction and expansion. And this is, in my view, this is
meaning discontinuous?
No, the scale factor is continuous, but it's not analytic. Okay. The derivative is discontinuous. So,
just
It's smoothed out on the string scale, but
just to add a model there, Robert, there is a kind of bouncing models that are not unstable and do not have these anisotropy problems, that they are motivated by pilot wave theory, the Broglie-Bohm theory, studied by Nelson Pinto Neto here at CBPF. And they reproduce all the main results of inflation with or without a scalar field. And they do describe the transition through the bounce, but through some kind of quantum effects that are only present in the Broglie-Bohm quantum theory. But I was asking about these ecpyrotics. So they are alive still, the ecpyrotic models.
yes.
That's what the point. Thank you.
And you see, in general, I don't give up on inflation either. So, but just if you want inflation, if you like inflation, you really have to go beyond effective field theory.
But there is always the singularity problem. There's both bouncing and emergent models don't have a singularity, so that's a plus, right?
Yeah, but I think in these attempts of Dvali et al. And Dasgupta et al. To get inflation out of going beyond effective field theory, I think that I know that in Dvali's work, you will not have a singularity either. But I have not worked on those. So, I mean, I take your point. You could say that even if you manage to save inflation, just inflation by itself seems to have a singularity problem.
Okay. Thank you very much, Robert.
All right. So very much, Robert, indeed, for this very interesting talk and some exciting new ideas. And I thank everybody for participating, for asking questions, and I hope to see you again in 1 week from now on our next online seminar. Thanks again, and stay safe.
Thanks again for the invitation and for listening and for the questions.
Bye.
And I hope to visit Natal sometime soon.
Oh, yes, absolutely.
It's a beautiful place.